Well, good evening or hello everyone. I am Beth Kimani, the AI ML track lead at Google Developer Groups, Chuka University, and today we shall be looking at the architecture of intelligence, and we shall basically be checking the perceptions from perception to agent AI. So today is going to be an interesting one because we shall actually have hands-on in the end. So yes, that is basically our today's session. So I think we shall start. So this is basically what we shall be using. This is going to be our roadmap. So we shall start with the atom, that is the artificial neuron, and then we shall do the activation functions and nonlinearity. We shall also do the feed-forward architectures, the calculus of learning, that is backpropagation, optimization gradient, modern frontiers, that is the transformer and agents, and then we shall try to build our own neural. We shall try to build our own neural network from scratch using just a few lines of Python. And yeah, that is everything we're going to do today. So yeah, I'm excited. So I think we should just start. Yeah. So uh, so yeah. So today is just about talking about software. We are talking about the architecture of intelligence. And in the last decade, we moved from machines that follow instructions to machines that learn from experience. But how does the learning actually work under the hood? So yeah, that's why the roadmap today. So if there's no problem, I think we just start with perception and that is the building block. So what do I mean by this? So uh, so what do I mean by the perceptron? So every skyscraper or every building that has more than one floor is made of bricks, right? And every network is made of perceptrons, and and it is inspired by the biological neuron and our mathematical vision takes inputs, that is X, and that is like the raw data, uh, and then it multiplies it by the weight, and the weight is just representing their importances, and also it adds the bias. So we had talked about this in our previous session on introduction to deep learning. So just a recap, just to revamp our brains on exactly what is happening. So think of it like a committee, okay? And each member is the input, right? Gives an opinion, but some members have more weight than others. Okay, so the basis of the committee's general tendency to say yes or no before the meeting even starts. So yeah, take the bias as the committee's general tendency to say yes or no before the meeting even starts, and then the result is a single number that determines the neuron fires. Okay, so yeah, uh, so we shall go to slide number 4, and here we're just going to talk on the activation functions. And activation functions are basically why non-linearity. This answers the question why non-linearity. But if we just added those numbers up, we just have a simple linear equation. Okay, so linear equations can't model the complexity of real world, like the curve of a human face or the number of nuances of language. So we need non-linearity, and how we can do this? We need we need non-linearity. So and how can we do this? Okay, activation functions are like the rectified linear unit, and and they act as a gate. And if the input is negative, the rectified linear unit uh, kills it, and it just turns it to a zero. And if it is positive, it just lets it pass. And this simple switch allows the network to learn complex, curvy, multidimensional patterns. Yeah, so we're going to look at the uh, layer hierarchy, and that is the flow of information. And um, the hierarchy is just the forward pass, and basically, just give me a second. And basically, we stack these neurons. When we stack these neurons, we create a hierarchy. So that is the input layer, which sees raw pixels, and then the hidden layer. And the hidden layer are the black box, and that is what we shall be trying to handle today. And the first layer might detect edges, and then the second might detect the eyes, and then the third might detect the face. Okay, so and then we do have the output, and the output just gives us the final probability. And what do I mean by this? It gives us a 99% chance that if you're checking, like for example, if something is a cat, it's going to give us the final probability that there's a 99% that this is a cat. So, and this is the forward pass generally. So data flows from the left to the right, being transformed at every step by matrices multiplication. And this is a massive, high speed calculation that turns raw data into abstract concepts. So, yeah, that's just it. There's nothing much to learn from there. So we should just look at the engine room, and this is where calculus now comes in. And we're just going to look at the the loss and the back propagation. This is just a quick revamp of what we talked about in the last session. So you just don't you worry, because it's basically sorry, let me just return to, let me just open, sorry about that. um yeah, so uh, sorry, I'm so sorry about leaving. I think you what, you went slide 7, right? Yeah, so here is where we shall look at the loss and the back propagation. And this is where how we look at how does the network know it's wrong, and we use a loss function. And okay, when a network okay, we're answering the question, how does the network know it's wrong? And this is where we use our loss function. So if network guesses dog, then it's actually when it's actually a cat, sorry, when it's actually a cat, the loss function calculates the cost of that error. Okay, so yeah, so to fix this, we actually do look at the back propagation, uh, and this is where the calculus comes in, and this is where we use the chain rule. So we walk backward from the error to the very first neuron, and it just calculates exactly how much each specific weight contributed to the mistake. And this is the mathematical version of assigning blame, and so we can make precision very much correctly. So yeah, so this is basically what I was talking of, where we just use the chain rule to calculate the gradient of the loss with respect to every weight. So, and this just allows us to assign blame for the error to specific weights across the entire deep architecture. Great. So, um, hope we are at par up to there. So we should just check on the gradient descent challenges, sorry, and I think we should just move so fast because I want us to like focus on how to like build our first neural network, and to feel happy and proud that you have actually come up with a first neural network. So once you know who to blame, we use the gradient descent. So here is where you like we go back propagation, or we go back up to the first neuron where the challenge happened, and then once we have understood what exactly has happened, that is where now we integrate the gradient descent. And what do I mean by gradient descent? So we know who to blame right now, okay? So we use gradient descent to update the weight. So imagine you're on a foggy mountain. I love using this example. So imagine you're on a foggy mountain and you find a valley. So you feel the slope with the feet, and you take a step downwards. So the size of the step is your learning rate. So if you take a big leap, you're learning in a big rate. So if you take a small leap, you're actually taking a lower learning rate. So, but as networks get deeper, we actually do hit a wall, and that is what we call the vanishing gradient. That is what we call the vanishing gradient. So, say in 100%, in 100 layer network, the signal can get so small that it disappears before it reaches the start. And to solve this, we use the rest net, and the rest net just what rest nets do is they actually they basically just um, skip connections, and they act like express elevators for data, allowing the gradient to bypass layers and actually stay strong. So yeah, so um, so we have talked of vanishing and the exploding. So let's go to deep learning for vision, and this is actually where we look at the modern frontier. So this is where we're going to look at the CNN and the transformers. So this is where we are going to actually get a bit of hands-on experience before we actually connect that to the responsibility of depth. So yeah, so in a real world, data has structure, and for images we use the convolutional neural networks, that is the CNN, and they actually do use filters that slide across the image looking for patterns regardless of where they are, right? And for a language, we moved from RNN to actually transformers, and the breakthrough here is actually attention. So a transformer doesn't read a sentence word by word, but it looks at every word simultaneously, and pays attention to the most relevant ones. So what do I mean by this? And How exactly does this work? So how okay if you look at ChatGPT or Gemini, this is what allows, say for example, GPT-4 and its successors to understand context across thousands of words. So if you actually do check if we actually do look at the agentic AI, so now that you're in 2026, we are entering an era of agentic AI, and we are moving beyond simple predictions. So these models now use the chain of thought. So it connects one thought to another thought just to reason through problems, and they use tools like calculators or web browsers to solve these tasks. So, and they build world models to predict consequences of their actions, and they aren't just talking; they are actually doing. So they do the talking, and they actually do the doing. Yeah. So, in conclusion, as we wrap up the uh, theory part, we shall actually have a simple wrap up. Then we shall actually do hands on, and that's the most interesting part of this learning. So um, we shall look at the responsibility of depth. And so, as we wrap up the theory part, we must address the black box. So, as these models get deeper, they become harder to interpret, and we face challenges with bias and fairness, and also the aspect of interpretability, and also energy consumption. So, uh, what do I mean by all this? So, the future of deep learning isn't just more layers, it's about neuro symbolic AI that is combining raw, that is like um, the intuition of neural networks with the logic of traditional programming. So, we are building the most powerful tool in human history, and our job is to ensure that as it gets deeper, it also gets safer and more aligned to human values. So yeah, let's try see if we can do a hands-on and how much we can do. So we shall let's make this as interesting as possible. So we shall build a neural network from scratch, and we shall use a very few lines of Python, and we shall simulate the forward pass and the loss calculation for simple classification tasks. So we shall be decoding. For a simple classification task, we are deciding if a fruit is an apple or is an orange based on the weight and the texture. So the setup, our setup will be, so the setup is our mini brain, and we shall build a single neural model. So the inputs x, the weights will be from 0 to 1, and the texture will be 0 is smooth, 1 is bumpy. The target is 0 for an apple, and 1 for an orange, because obviously with texture being smooth, an apple is more smooth compared or is smoother compared to an orange. So yeah, we can run this in any Python environment. So you can do this using Google Colab or Jupyter Notebooks, or even locally using the uh, IDEs like VS Code. But I think I shall work with VS Code, because I am conversant mostly with VS Code. So, no, I mean with Jupyter Notebooks, sorry. So I'll just close this tab. So use whichever you're comfortable with. Then we should just start. So let's wait for that to load. So yeah, let's just create new. Then we should create a kernel. Uh, so yeah. So first we shall import the relevant libraries. So that's what we do, and then we shall do the data to check on the weight and the texture, and then we shall initialize the knobs, that is the weights and the bias. So usually random, but let's fix up starting values, and then we shall do a calculation of the weighted sum, and then we shall do the loss. So that we just calculate how wrong we are, and then we shall do the manual learning. So deep learning just is just like the process of changing the weights to make the loss smaller. So we shall try the hands-on, and then we shall just stay simulated. So yeah, let's see how much we can achieve in this. And yeah, so we're just going to import relevant library. So import numpy as np, as np. So we just run that, and then we just do the activation function. So what we're doing here is the activation function. Activation. The activation. Sorry. sorry, the activation function. So let me just add another cell, and this is where we shall do the initializing. So sorry, I'm so sorry. So initializing the knobs. So and then from there we should just do the calculations. So calculations, and then from there we shall just check the loss, so how wrong we are. So just give me, so how wrong, how wrong, sorry, just how wrong are we? Yeah, so hope I'd run this. Oh, just cut this. Hope I had run. Yeah, okay, it's running. So we shall try to calculate or find the activation function, and this is actually we shall use sigmoid. So so from here we should just define sigmoid. So def sigmoid, and we just give it the value x, and then we just return 1. So you remember we said 1 is roughness and 0 is smoothness. So return 1, and we shall multiply that with 1, then add that to np dot exp in brackets negative x. Yeah, so that's it, and then we run this. Yeah, so we shall try to do the initialization of knobs, and no, we shall actually sorry, I forgot. Let me just add a cell. So this is where we shall actually fit our data. So let me just put the data. So this is where we shall check the weight and texture. So weight and texture. So yeah. So let's get to coding. So we said let's just define everything we said. So we said for apples, we shall equate the apple to, say, let's give it an array of 0.2 and 0.1. So yeah, and then for the orange, we shall just equate this to we shall just equate this to like a 0.9. So in terms of roughness, so 0.9 and 0.8, because they can't be completely rough. So yeah, so let's put the inputs. So input, so give it the variable inputs, and then we just say np dot arrays, and then you just put that into square brackets, so 0.9, 0.9 and 0.8. So yeah, Oh, I have an error. Let me just np.array array delete that and then close the brackets. Yeah, so and then we assign another variable, which is our target, and our target, we should just equate it to 1.0, and we just want the network to guess orange. Okay, so we can put that so guess orange. Yeah, so let's run this, see if we have any errors before we proceed to initializing knobs. So here we shall check the weight and bias. So yeah, our main topic is weight and bias. Great. So here it is usually but it is usually very random, but let's pick some starting values. Okay, so we shall assign variables weight and bias. So we say weights, and we say our weights will be np.array, and we should just equate that to 0.5, sorry, a 0.5, and a negative 0, sorry, 0.21. Yeah, and I think I have an error, so we should do that. Yeah, that. And then from there we just assign a bias, so we just say bias, and we just equate that to a 0.1. Yeah, so if we run, let me see. Oh, got to put the equal sign. Great. So if I run this, we're actually able to, yeah. So we shall do the calculation, and this is where we actually check the weighted sum. So here's where we do check the weighted uh, the weighted sum. So what do I mean by checking the weighted sum? Oh, sorry. Let's just let's check the results. I forgot to do that. So we just print let's do this. And then we just say starting. Just say let's put that in caps. Starting forward pass. So oh god. So yeah. So let's run this. Great. So we shall do the calculations, and this is where we check the weighted sum, and we shall do the sum. Let me just put so our sums will actually be equal to times 1 weighted sum multiplied by the input, so x1 multiplied multiplied by weighted 1, and then we add, and let me just paste this because we shall actually do a lot of repetition. So our x2 weight by our x2, sorry, our input multiplied by our weight, and then we add the bias. I hope you remember the formula. So yeah, it will be that way. So let's give the variable, let's assign the variable weighted sum, and we just equate this to np np dot dot then you just say inputs inputs comma just say weights, and then we just add this to, oh, we just add this to bias, and then just do a predicted a prediction, so sorry, prediction, and our prediction will actually be sigmoid. Sigmoid, just do the weighted sum. So this, Control C, then you just paste it here. So if we print, so if we print, let me just put F. So if we print the weighted sum, just this, just start with some caps, and the sum should also start with caps. Weighted sum, which is our Z, just say trophy, and then just make sure it's into 4 decimal places, so 4F. Great. So if we run this, we actually see our calculations for the weighted sum is a 0.3820, and we shall print something else. So we shall actually print the network prediction. So let's see what happens when we do a prediction. So we print, sorry, so network prediction, prediction. If we do a network prediction, where 0 is equal to apple, and we said 0 is equals to an apple because of softness or smoothness, and 1, so we're just running a game of probability, and 1 is just equal to orange, so because an orange is rough on the outer part. So yeah, so we just put the brackets, and then we do the prediction of the, we do a prediction, and then we just put this equal, we just confine that to 0 decimal places. So yeah, let's see if we need to debug anything. Don't think we need to debug anything in this line, so let's run that. So yeah, you actually able to see that the weighted sum, that is the z, is 0.3820, and the network prediction is actually a 0.5944, so an estimate of 0.6. So yeah, let's see how wrong we are. So let's calculate the loss. So in brackets, we're just doing the loss. So we just sorry, doing, excuse me, we're just doing the loss. So let's assign a variable loss, then we just equate this to target. Uh, equate this to target minus uh prediction. So we had our target, and we had what we predicted. So and then we just multiply. We just raise this to power 2. Okay, so yeah, then if we print this, so print current loss, so f, so current loss, current loss, um and we just say our loss is we just equate this to loss, and confine it to 4 decimal places, so 4 for f. Yeah, so if we run this, I started with a capital letter, so let's run this. Yeah, so our current loss, so if we do a minus of the prediction and the if we do let's just use the calculator and see if actually that's it. So I'll just use my phone's calculator. So 0 point sorry sorry 0.5944 0.38. Yeah, so basically that's it. So here uh, we've actually created our own neural network. So using that simple way, very interesting way, we just come up with our own small neural network. And deep learning is just the process of changing the weights to make the loss smaller. So I'll I'd urge you to like try the like these 3 hands-on, where you change the weight. So look at the code. So if you change the weight from here, so if you actually check the np.array here, and then we check so this is the weight, right? So what happens to the prediction, and the observation is the prediction should get closer to 1, and that is the orange. And sorry, it should get closer to 1, and the loss will actually drop. And that is why if you check at the loss has actually dropped to something close to 1 to 0, and that is a 0.1645. So if you change the input, so if you change the inputs to like a 0.1 to we give it the list of 0.1 and 0.2, a small soft fruit. So the observation is the network will likely still gets closer to an orange because the weights are currently biased biased towards higher numbers, and it needs training to learn the difference. So break the neuron. This is where we set the bias to a negative 10.0, and here is where the observation will just be, the prediction will drop to almost zero, and the bias is so negative and it inhibits the neuron from firing. And no matter how strong the inputs are, still uh, it's still the bias will still be so negative. Yeah, so what we just simulated is a real world deep session, and we would automate a two-step using gradient descent. So instead of typing the new weights, the computer just calculates the slope of the loss and slides the weights down that slope automatically. So the deep challenge is, what if we take this further and we try to ascend, we try a second neuron. So how would you pass the prediction of a neuron, of neuron 1 into the second neuron? And that is the birth of a hidden layer. So um, we shall try do a back propagation. So give me 1 second. Uh, we shall try do a back propagation on this, and see how this goes. So we shall actually transition from actually just watching a neuron to actually training. And this is the interesting part, and this is the heart of the depth of the planning. So in this hands-on, we shall actually implement back propagation and the gradient descent. So we're not just going to guess the weights anymore. We are going to write the code that allows the neuron to feel its own mistakes and feel them. So here's the trainer code. So we are actually just going to do a revamp of this. So we have actually imported the relevant variable, that is the import numpy as np. We have set up. So we shall actually just improve this from what it is to something greater. So yeah, let's try this and see what happens. So we just sorry, let's just do an AI of this, and just give me 1 second. So 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 if we actually do a setup, so let's just control all. Sorry, oh no. So control C. So here we should actually just try to uh just change it a little bit to something more hands-on. So let's see. So df is sigmoid x return 1 with that. So from here we shall actually have another line that says def sigmoid just give me 1 second. See if we can actually connect Okay, it's fine. It's just too sigmoid. I'm just really lazy to do it. Uh, sigmoid derived derivation. Sorry, so derivative, and we just put that equal to x, and we just return um, x. I'm just going to change this. Control C. Control. So we're just going to change a few variables here. So x, uh, and then this will be multiplied. Uh, multiplied by 1 minus x. So yeah, 1 minus x, and this is just the slope for the chain rule. So yeah, and then we should just do a data. For the data, as you can see here, for our data, we just equated all this to the weight and texture, and we're actually just going to change this to an array. So same variables, but now we're going to use x and y. So let's just run this. Yeah, so let's just copy this, and we just paste it